Beneath the rust-coloured sands of Mars, a Chinese rover just uncovered something that shouldn't exist. 76 mysterious underground layers that are forcing scientists to completely rewrite the history of water on the red planet. And if the timeline for liquid water just changed, then so did the timeline for life itself. For decades, the scientific consensus was clear. Mars is a frozen desert, a dead world where any chance for life ended billions of years ago when its atmosphere vanished and liquid water disappeared forever. But China's first interplanetary mission, Tianwen-1, just shattered that comfortable assumption. Hidden beneath the dusty plains of Utopia Planitia, instruments detected something nobody expected. Evidence of ancient flooding, massive deposits of buried ice, salty mineral crusts that could only form in the presence of liquid water. And most shocking of all, geological features suggesting this water existed far more recently than anyone thought possible. If liquid water persisted on Mars into the recent geological past, then the window for life didn't slam shut billions of years ago. It might have stayed open much, much longer. Perhaps long enough for something to evolve, to adapt, to survive in the freezing darkness beneath the surface. So let's dig into exactly what China found, why it changes everything, and what it means for the search for life beyond Earth. The story begins on July 23rd, 2020, when China launched its most ambitious space mission to date. Tianwen-1, meaning questions to heaven, was China's first fully independent interplanetary expedition. A single spacecraft carrying 3 critical components: an orbiter, a lander, and a rover, all designed and built domestically without foreign assistance or NASA blueprints. After 7 months crossing the void between Earth and Mars, Tianwen-1 entered Martian orbit in February 2021. For 3 months, the orbiter mapped the surface below, identifying the perfect landing zone and testing communication systems. Then on May 14th, 2021, history happened. The lander separated and began its descent through the thin Martian atmosphere, touching down in Utopia Planitia, the same vast plain where NASA's Viking 2 had landed 45 years earlier. Rolling off that lander came Zhurong, named after the ancient Chinese god of fire. Standing 1.85 metres tall and weighing 240 kilograms, it became the first non-American rover in history to successfully operate on the Martian surface. The mission was designed to last 90 sols, roughly 3 Earth months. Instead, Zhurong exceeded all expectations, operating for over a full year. It covered nearly 2 kilometres of Martian terrain, scanning, sampling and transmitting data before entering hibernation in 2022, when thick dust accumulation and the brutal Martian winter drained its solar panels. A modest achievement on paper. But what this little rover discovered beneath the surface has veteran planetary scientists completely rethinking Mars. Zhurong carried something previous Mars rovers lacked: a ground-penetrating radar system capable of seeing 10 to 35 metres deep into the Martian crust. And when scientists analysed the radar data, they saw something that had never been observed before. 76 distinct horizontal layers buried beneath the dust. Each layer represents a different environmental period. Maybe a flooding event, maybe an ice sheet advance, maybe a period of heavy atmospheric dust deposition. But the pattern was unmistakable. These weren't random geological features. They were cyclical, repeating, rhythmic. Scientists from the Chinese Academy of Sciences concluded these layers point to episodic flooding events, periods where subsurface ice melted, flowed across the surface, then froze solid again. And this cycle repeated over and over across hundreds of thousands of years. But the radar data was just the beginning. Zhurong's other instruments detected minerals that only form in the presence of liquid water: hydrated sulfates, salt deposits, chemical signatures that told a very specific story. These minerals create thin, salty crusts on the surface. And here's why that matters. Salt water, or brine, has a much lower freezing point than pure water. Even in Mars's freezing temperatures, salty brines could remain liquid just beneath the surface, trapped in those mineral crusts like water in a sponge. Then there were the dunes. The textures and patterns in the sand told yet another story. Signs of recent glacial activity. Reshaped sand patterns, cracked surface crusts, smoothed ridges that likely formed as recently as 400,000 years ago. 400,000 years? To put that in perspective, that's not ancient in planetary terms. That's practically yesterday. That's when early humans were already walking on Earth, making tools, controlling fire, building shelters. For decades, the accepted timeline said Mars's last liquid water vanished 3 billion years ago. Zhurong's discoveries just moved that timeline forward by billions of years. The implications are staggering. If liquid water existed on Mars as recently as a few 100,000 years ago, then potentially habitable conditions persisted far longer than we thought. The window for life didn't close in Mars's distant past. It might have flickered on and off, like a dying ember, well into the planet's recent history. And that changes the fundamental question we're asking. It's no longer whether Mars ever had water and life. It's how long conditions remained favourable, and whether something might still be surviving in the cold darkness beneath the surface. This isn't the first time we've searched for life on Mars. Nearly half a century before Zhurong's landing, humanity made its first serious attempt to answer the ultimate question. In 1976, NASA's Viking 1 and Viking 2 touched down on Mars. Each lander carried a miniature biology laboratory, the first ever sent beyond Earth. The mission was simple but profound: scoop up Martian soil and test whether anything living existed inside. The biology experiment was elegant. Mix soil samples with nutrients labelled with radioactive carbon-14. If microbes were present and metabolizing the nutrients, they would release gas containing that radioactive signature. The instruments would detect it, and we'd have proof of extraterrestrial life. When the Vikings ran their tests, something remarkable happened. The sensors lit up. They detected gas release, chemical reactions occurring in the soil samples. Scientists were divided. Some argued this was definitive proof of Martian biology. Others insisted it was just unusual chemistry, not life. The debate centred on one crucial discovery. Mars's surface is saturated with perchlorates, highly reactive chlorine-based salts that can mimic biological signatures. Did Viking detect actual microbes, or just weird chemistry from these exotic minerals? The controversy raged for decades. Some scientists still argue that Viking did find life, but we killed it during the sampling process, before we could properly identify it. Others maintain the results were purely chemical reactions, with no biological component. We still don't know for sure, and that ambiguity makes Zhurong's discoveries even more important. Because now we know water persisted far more recently than the Viking era assumed. So why does water on Mars come and go? What drives these cycles of melting and freezing that created those 76 layers Zhurong detected? The answer lies in Mars's unstable orbit and the cosmic clockwork called Milankovitch cycles. On Earth, these orbital variations cause ice ages and warm periods. But Earth has a massive moon that stabilises our axial tilt, preventing wild swings. Mars has no such stabiliser. Its climate swings are far more extreme. First, there's orbital eccentricity. Every 100,000 years or so, Mars's orbit around the Sun changes shape. Sometimes it's nearly circular. Other times it stretches into a long ellipse, bringing Mars much closer to the Sun at one end of its orbit and much farther away at the other. When the orbit becomes highly elliptical, seasonal temperature differences become extreme. One hemisphere bakes in intense solar radiation, while the other freezes in the cold darkness. During those warmer orbital phases, buried ice can melt, creating those episodic flooding events that left behind the layered sediments Zhurong's radar detected. Those 76 layers might literally be a record of Mars's orbital heartbeat. One layer for every major swing in its eccentric orbit over millions of years. Then there's axial tilt, or obliquity. Right now, Mars tilts at about 25 degrees, almost identical to Earth, but unlike Earth, Mars's tilt isn't stable. Over hundreds of thousands of years, it can swing wildly between 15 and 35 degrees. When the tilt increases, sunlight reaches deeper toward the polar regions. Polar ice caps begin to melt. Water vapor and frost redistribute toward the equator. When the tilt decreases, the planet cools dramatically, freezing that redistributed moisture back into the ground. Zhurong's data, the mineral crusts, the frozen brines, the water-altered chemistry, all align perfectly with this pattern. Mars went through repeated cycles of melting and refreezing as its axial tilt wobbled through cosmic time. Finally, there's axial precession. As Mars spins, its rotational axis wobbles slightly, like a spinning top starting to lean. That wobble gradually changes which hemisphere points toward the Sun during different parts of the orbital cycle. It's a subtle effect, but over tens of thousands of years, it redistributes warmth across the planet's surface. That constant reshuffling helped spread water and dust, shaping the dunes and geological deposits Zhurong explored. Together, these three orbital variations, eccentricity, tilt and precession, act like gears in a cosmic clock. Each tick melts ice, shifts atmospheric patterns, and buries new sediment layers. Zhurong's 76 underground layers fit perfectly into this rhythm. They represent cyclical periods of warming and cooling. Each layer is a snapshot of a temporarily warmer, wetter Mars, repeating across hundreds of thousands of years. These weren't random flooding events. They were part of a planetary-scale heartbeat, the pulse of water appearing and vanishing through deep geological time. And if water kept returning, even temporarily, then the opportunity for life kept returning as well. The next chapter in China's Mars exploration is already being written, and it's arguably the most ambitious robotic mission ever attempted. Tianwen-3, scheduled to launch in 2028, will attempt something no nation has successfully completed: collect pristine Martian samples and return them physically to Earth by 2031. This isn't a single spacecraft. It's a coordinated system requiring two separate Long March 5 rocket launches. One will deliver an orbiter and return vehicle to Mars orbit. The other will send a lander and ascent module to the surface. Once on Mars, the lander will deploy an automated drilling system capable of collecting samples from multiple depths. Both surface dust and deep subsurface material will be sealed inside sterile containers to prevent contamination. Onboard instruments will conduct preliminary analysis, screening for organic molecules, hydrated minerals, and possible microfossil structures before the samples are even sealed. Then comes the hard part. The ascent vehicle must launch from the Martian surface, something only NASA has ever accomplished, and rendezvous with the waiting orbiter in Mars orbit. The samples transfer to the return vehicle, which then begins the long journey back to Earth. If successful, this would deliver humanity's first physical Martian rocks directly into our laboratories. Not images, not sensor data. Actual pieces of Mars we can hold, analyse and study with every tool modern science possesses. Chinese scientists have identified 86 potential landing sites, focusing heavily on two regions. Utopia Planitia, where Zhurong made its groundbreaking discoveries, and Croix Planitia, home to ancient dried river deltas and lake beds. These are geological treasure zones where biosignatures, the chemical fingerprints of past life, are most likely to be preserved if they ever existed. And here's what makes this mission geopolitically significant. China says the returned samples won't be kept secret. The mission is designed for international scientific collaboration, with researchers worldwide expected to analyse the material together. If Tianwen-3 succeeds, it could beat NASA to the punch by years. NASA and the European Space Agency plan to retrieve Perseverance rover's cached samples by the early 2030s. But that mission has been plagued by budget overruns and technical setbacks. Current timelines are in serious doubt. That creates a narrow but historic window. If China's samples reach Earth first, and if they contain even trace evidence of organic chemistry or fossil microbial structures, it would be absolutely revolutionary. For the first time, we wouldn't just be examining Mars through cameras and remote sensors. We'd be holding actual pieces of another world in our hands, perhaps holding the answer to whether life ever existed beyond Earth. But while Zhurong hibernates beneath Martian dust, back on Earth, China has been building something equally fascinating: Mars on Earth. In Gansu province, on the edge of the Gobi Desert, sits Mars Base 1, a $61 million facility constructed in 2019 featuring realistic red sand hills, pressurized habitat modules, and experimental greenhouses. Originally designed as both a training facility and educational attraction, Mars Base 1 hosts students and astronauts in training, practicing what life on the red planet might actually require. Mock airlocks, simulated solar power systems, even artificial dust storms replicating Martian conditions. Further west in Qinghai province's remote desert lies Mars Camp, a far more rugged installation. Unlike Gansu's polished domes, this facility resembles a frontier outpost. Clusters of metallic modules and repurposed containers arranged for maximum functionality, not aesthetics. Here, engineers and recruits practice survival skills, isolation management, resource rationing, critical system maintenance, all the unglamorous realities they might face 200 million kilometres from home. Together, these terrestrial Mars bases represent the first phase of China's long-term colonisation strategy, building the psychology and institutional knowledge before building the actual mission. And the roadmap is already drafted. China's space agency has outlined 5 crewed Mars missions spaced roughly 2 years apart: 2033, 2035, 2037, 2041, and 2043. Early missions will validate life support technology, test landing systems, and demonstrate ascent capabilities. Later missions aim to establish permanent surface habitats and develop in-situ resource utilisation, extracting oxygen and fuel directly from Martian atmosphere and soil. To enable this, Chinese engineers are developing nuclear thermal propulsion. Not science fiction, but actual working technology already in development. Nuclear engines could double the efficiency of chemical rockets, cutting Mars transit time nearly in half, while providing continuous power for crew systems. But propulsion is only half the challenge. The other half is logistics. Moving the sheer mass of equipment and supplies into Earth, orbit before sending it to Mars. That's where China's most ambitious concept emerges: the space elevator, or sky ladder. A theoretical structure using ultra-strong carbon nanotube cables stretching from Earth's surface to low orbit. Cargo would ascend mechanically, lifted by electromagnetic climbers powered by ground-based systems. No rockets, no fuel, just gravity, counterweight physics, and material science. It sounds impossible, but so did reusable rockets before SpaceX. So did landing on the moon's far side before Chang'e 4. Both seemed like fantasy until they became reality, and China accomplished both. Meanwhile, on the other side of the Pacific, another competitor races toward the same goal. Elon Musk and SpaceX envision a self-sustaining Martian city of 1 million people by around 2050, transported by fleets of starships carrying 100 tons of cargo each. The approaches couldn't be more different. China's strategy is centralized, methodical, and state-driven. Fewer public updates, lower risk tolerance, but massive coordination between government, military, and industrial sectors. SpaceX operates on rapid iteration and transparent testing, public failures, fast learning, trial and error conducted in full view of the world, different philosophies, same fundamental bottleneck: how to move enormous mass into orbit and then across the interplanetary void to Mars. Whichever system cracks that problem first, whether reusable chemical rockets or electromagnetic launch systems, could define the next century of space exploration. The next great leap is already scheduled. By 2031, Tianwen-3 will attempt to return the first Martian samples to Earth. Inside those tiny sealed capsules might lie the answer to one of humanity's oldest and most profound questions. Are we alone? If China brings back the first physical evidence of life beyond Earth, even a single microfossil, even a complex organic molecule, even a hint of biological chemistry, history books will mark that moment forever. But the story doesn't end with sample return, because as China prepares to bring Mars home, they're simultaneously preparing to go there permanently. The discoveries Zhurong made beneath the Martian dust changed everything. Those 76 layers aren't just geological curiosities. They're proof that Mars's story isn't over, that water kept returning, that conditions kept changing, that the window for life stayed open far longer than we ever imagined. And if liquid water existed as recently as 400,000 years ago, then maybe, just maybe, something found a way to survive in the frozen darkness beneath the surface, sheltered from radiation, protected from the thin atmosphere, living in the liquid brine trapped between rock layers. We won't know until we dig deeper, until we drill into those subsurface layers and examine what's hiding in the Martian underworld. And China is preparing to do exactly that. The question now isn't whether they'll search for life on Mars, it's whether they'll be the ones who find it first.